Imagine you have a piece of paper with a strict width limit. You are given a long string of letters and a specific width for every single letter. Your challenge is to figure out exactly how many lines you need to write the whole string and how much space is used on the very last line. Take a moment to think. How would you solve this without a computer? Let's break this down from the very beginning. We have two main inputs. First, we have a list of numbers, 26 of them, representing the width of every letter from A to Z. For example, the first number is the width of A, the second is B, and so on. Second, we have a string of text, like a sentence or a paragraph, that we need to write down. The rule is simple but strict. Each line on our paper can hold a maximum of 100 units of width. If a letter fits, we write it. If adding that letter would make the line wider than 100, we cannot write it on the current line. Instead, we must move to a brand new line and start writing there. Our goal is to output two numbers. The first number is the total count of lines we used. The second number is the exact width used on that final last line. Why is this tricky? Because we cannot just count the letters. A line might have 10 A's but only 5 W's. The width varies. We have to simulate the writing process, letter by letter, keeping a running total of how much space we've used on the current line. If we mess up the math even once, we might put a letter on the wrong line, throwing off the entire count. We also have to remember that we always start on the first line, so the minimum answer is always one line, even if the string is empty or just one letter. The constraints tell us the string can be long, so we need a method that doesn't get confused or slow down as the text gets longer. We need a way to track our progress through the text while constantly checking the width limit. The obvious thing to try is to simulate the writing process exactly as a human would do it, but perhaps in a very inefficient way. You might think, I'll just write the whole string on one giant line first, then go back and cut it up into chunks of 100. Or, you might try to check every possible combination of letters to see which ones fit together. The naive approach often involves repeatedly scanning the string or recalculating the width of segments from scratch every time you move to a new line. For instance, if you decide a line is full, you might restart your width counter from 0 and scan the remaining letters again to see how many fit on the next line. This is redundant work. You are rereading the same letters multiple times. You are forgetting the progress you already made. In computer science terms, this is like trying to fill a bucket by pouring water in, checking if it's full, then emptying it and starting over, rather than just keeping the water in. This repeated scanning makes the process very slow. If the string is very long, you end up doing a massive amount of unnecessary calculation. The time complexity of this inefficient method would be much worse than linear, potentially growing quadratically, meaning if you double the text, the work quadruples. The space complexity might also be high if you are storing temporary chunks of the string over and over again. We need a smarter way that remembers exactly where we are and only looks at each letter once. The key insight here is that we don't need to look back or rescan. We only need to look forward one letter at a time and keep a running tally. We can solve this in a single pass through the string. Imagine you are walking down a hallway with a backpack. You have a limit on how much weight you can carry. As you pick up each item, you check if adding it to your backpack exceeds the limit. If it does, you put the item down in a new backpack and start fresh. You never need to go back to the previous backpack to check its weight again. You just remember the count of backpacks used and the weight of the current one. In our code, we start by declaring two variables. The first is a counter for the number of lines, which we initialize to 1 because we always start on the first line. The second is a variable for the current width of the line we are writing on, which starts at 0. We also define a constant for the maximum width allowed, which is 100. Then, we begin a loop that goes through every single character in our input string, one by one. Inside the loop, we first find out how wide the current letter is. We do this by looking up the letter in our list of widths. Since the list is ordered by the alphabet, we find the position of the letter and grab its width value. Next, we perform a critical check. We add the width of the current letter to our current line width. If this new total is greater than the maximum allowed width, it means the letter does not fit. So, we increment our line counter by 1 to move to a new line. Crucially, we reset our current line width to be just the width of this new letter, because it is now the first item on the new line. If the letter does fit, we simply add its width to our current line width and continue to the next letter. We repeat this until we have processed every letter in the string. Finally, we return an array containing our total line count and the final width of the last line. This approach ensures we touch every letter exactly once, making it incredibly fast and efficient. Let's trace this step by step with our example where every letter has a width of 10 and our string is the entire alphabet from A to Z. We start with our line count set to 1 and our current width set to 0. The maximum width is 100. We pick the first letter, A. Its width is 10. We check. 0 plus 10 is 10. 10 is not greater than 100, so we add 10 to our current width. Now line count is 1 and current width is 10. Next, we pick B. Its width is 10. We check. 10 plus 10 is 20. 20 is not greater than 100. We add 10. Now line count is 1 and current width is 20. We continue this for C, E, F, G, H, I, and J. Each time we add 10. After J, our current width is 100. Line count is still 1. Now we pick the letter K. Its width is 10. We check. 100 plus 10 is 110. 110 is greater than 100. This letter does not fit, so we increment our line count. Line count becomes 2. We reset our current width to just the width of K, which is 10. Now line count is 2 and current width is 10. We pick L. Width is 10. 10 plus 10 is 20. It fits. Current width becomes 20. We continue this pattern. We add M, N, O, P, Q, R, S, T, U. We keep adding 10 until we reach the letter T. At T, we have added 10 letters on the second line, K through T. That is 10 times 10, so current width is 100. Line count is 2. Now we pick the letter U. Width is 10. 100 plus 10 is 110. This is greater than 100, so we increment the line count. Line count becomes 3. We reset current width to 10 for the letter U. Now line count is 3 and current width is 10. We pick V. Width is 10. 10 plus 10 is 20. Current width becomes 20. We pick W. Width is 10. 20 plus 10 is 30. Current width becomes 30. We pick X. Width is 10. 30 plus 10 is 40. Current width becomes 40. We pick Y. Width is 10. 40 plus 10 is 50. Current width becomes 50. Finally, we pick Z. Width is 10. 50 plus 10 is 60. 60 is not greater than 100. Current width becomes 60. We have reached the end of the string. Our final line count is 3, and our final current width is 60. And there's our final result. The algorithm tells us we need 3 lines to write the string, and the last line uses exactly 60 units of width. This is correct because the first line held 10 letters, the second line held 10 letters, and the remaining 6 letters fit on the third line. You'll spot this pattern whenever you are processing a sequence of items and need to group them based on a running total or a capacity limit. Look for problems where you have a container with a fixed size, and you must decide when to start a new container based on whether the next item fits. The time complexity is linear, or O of n, because we look at each character exactly once. The space complexity is constant, or O of 1, because we only use a few variables to store the counts and widths. Try the next problem on linear scanning to practice this pattern. Don't forget to subscribe for more beginner-friendly algorithm breakdowns.